Hey, this is Mr. Worden. I'm getting you guys a tutorial on motion graphing. This goes with our Unit 1A in physics. A couple different days worth of content put together, but hopefully this is helpful reminders if you need to review or study or if you're out and just trying to make this up from home. All right, so getting started. You guys are going to be able to, by the end of today, create and interpret motion graphs. They come in stacks. We're going to kind of work with that. We're going to break them down in terms of the patterns that you're going to see over and over again, at least at our level of physics. We're going to take a multi-step graph. We're just going to break it up into chunks and divide it and deal with one piece at a time. That'll make things a lot easier. We're also going to make sure that you understand where these shapes are coming from that we're talking about and how this relates to our equations, which coming up after motion graphs, we're going to start using to solve some word problems with. Lastly, we're going to give you like a tiny preview of some calculus concepts that'll help make your life a lot easier. Not like crazy hard calculus, just real simple beginner stuff that I think is going to go a long way towards understanding these things. So before we get going, let's just talk some vocab. We're going to use the words distance and displacement mostly interchangeably. There's a little bit of a difference. With a vector concept, you're worried about not just how much, but also in which direction. So for example, if I say 10 miles an hour, that's different than if I say 10 miles an hour north, or 10 miles an hour south, or 10 miles an hour up. By putting that direction on there, it's a little more specific. It gives you more information. So a vector always has more info to it than a scalar does. Like, most people think it's okay to go 60 miles an hour on the freeway. And normally I'd agree with them, but what if you're going 60 miles an hour on the freeway in the wrong direction? So we take a lot of vectors for granted. They are important. A little bit of a difference. Same thing, speed and velocity, they mean almost the same thing. Velocity is just a little more specific. Lastly, a lot of the time our acceleration will be defined in terms of our velocity, which is already a vector. So that kind of implies that acceleration is a vector as well. As far as unit labels go, we're looking at meters, meters per second, and meters per second squared. With an acceleration, you've got a time squared on the bottom. If we're working in the standard system instead, I might ask you, well, if my car can go from 0 to 60 miles per hour in 6 seconds, then you could kind of simplify that, 60 over 6, and you could break that down to 10 miles per hour per second. You might hear hours and seconds there. That's another time squared concept on the bottom. That'd be if we're in standard units, but we're in metric, of course. So we're using meters, meters per second squared. Lastly, at the point when we get to the equation-based problem solving, we're going to be looking at some variables, and you're going to see variables that kind of basically match up with the name of the concept they're describing. Pretty common. So we're going to be using D for distance or displacement, V for velocity or speed, and A for acceleration. At some point, we'll switch to two-dimensional problem solving. We'll start introducing X versus Y as different as well. So that's just some kind of terms and conventions there. All right, now here's my first question for you guys. These are distance or displacement graphs. They're asking, where is the object? Where is the position? So first of all, you might look at any of these graphs and see that the origin, 0, 0, is right when you start tracking things, right when time is 0. You haven't let any time elapse yet. That's going to be always our x-axis on these, time. Then also, that'll give you the starting position. So the y-intercept, where it hits this y-axis, which in this case is distances, that's where did the object start out. And this one is starting from the origin. So like basically you're saying this one's coming right from whatever I'm defining the starting point as. It hasn't moved yet, and we haven't let any time elapse. Now, what you're hopefully looking at is there are 3 different patterns on here. We might call this first one just totally flat across. And sorry, my head's right in the way. Let's see what we can do here. All right, so right here, whatever this position is at this point in time, we wait a little while later, position is still in the same spot. We wait a little later, position still in the same spot. We wait a little bit later, position still in the same spot. So this thing's position or location has not changed over time. That means that this first graph describes something that is completely stationary. And you're going to see a pattern like this a lot. On a distance graph, if you see a flat section, that means that the object is not moving over that whatever time period that is. Now the second one here, over time, it moves some amount. Over time, same chunk of time, it moves the same amount. Same chunk of time moves the same amount, same chunk of time moves the same amount. Hopefully you're getting kind of a rise over run idea that's bringing back memories of slope and your IM1 classes. But basically this one is moving over time and covering the same distance each time interval. This is moving at a steady rate. So we're going to call this one constant velocity, meaning that the speed of this object is not changing anywhere in that graph. So anytime you see kind of a diagonal uphill or diagonal downhill, that means that the speed isn't changing. its position is changing. Like, yeah, it's definitely in a different location than it started, but it's changing at a steady rate. Lastly, this third one over here, this is changing more and more and more over time. This is an indication that there's acceleration. This is speeding up, and so it's not just moving, it's also moving more and more and more. You could also get a pattern where you're moving less and less and less, but either way, what you're going to get is a curve. So if you see a curve on a displacement graph, it's an indication that it's somehow accelerating. So these are the three basic scenarios we're looking at. I like to call this one parking lot, this one is freeway, and this one is on-ramp or off-ramp. This is where your speed is changing, this is where you're keeping your speed, this is where you're not moving at all. So we're just looking for those three basic patterns. Now this can happen in a couple different forms, so there is more than one way for this to happen. And that's why I would like you guys to pause the video at this point and just try to explain to yourself what each of these three graphs is describing. One thing that'll help you guys get good at graphing is developing your inner monologue, your kind of metacognition and thinking around these. And one way to do that is kind of by talking your own way through it, whether that's out loud or in your head or whatever you're comfortable with. So please pause the video and in your best own words, try to describe each of these three scenarios, what's happening in these graphs, all position graphs. Pause right now, do that. Alrighty, let's check what you guys are thinking. So first up, on scenario 1, this is an object it's not moving. We can tell that because no matter when we check, the position value is always the same. And what's different about this graph is that it has a negative position value. So let's do some thinking on this. Okay, if I put myself at the origin, I would call positive positions things that are in front of me. That means that if this has a negative position value, I'm defining it as somewhere behind me. So that would be one way to think about this, that instead of an object way far away in front of me, this is an object way far away behind me. Regardless though, it is not moving. Definitely that's the most important thing to take away from scenario 1. Now along those same lines, in scenario 2, if I put myself at the origin and positive values are in front of me, this object starts out way, way, way in front of me. Later on, it's actually right at wherever I am. It's no longer in a different spot than I am. So this went from way far in front of me, getting closer and closer and closer until it's right where I am over time. So I would say this thing has started out far away from me and is coming back towards me. How is it doing that? At a steady rate. We're seeing just a continuous downhill slope. And so that's telling me over time, it's changing distance by the same amount. We're moving at a constant velocity. In this third scenario, we also have an object far out in front of me, moving back towards me, getting closer and closer. But it starts out in a short amount of time, changing a big distance. This thing starts out really, really fast. Okay, so a big drop in distance in a small amount of time. Later, in a large amount of time, the distance barely drops at all. That's an indication that later on, this thing is hardly moving. In fact, by the end, it may even be stationary. It may have come to rest, which would be how we'd say that in physics, just because of old school thinking there. So this is starting out fast, it's slowing down, and the entire time it was in front of me, but I would say that it's moving backwards towards me. Distances are decreasing. All right, check how you did. Hopefully you're able to explain those and it kind of makes sense. And we'll keep going. All right, now one thing we can do with graphs is we can kind of take the descriptions, we can look at some different chunks of stuff, and we can try to figure out what's going on. And we can also divide this up to where we're not solving everything at the same time. Instead, we can break this into some pieces. So I'm gonna grab a whiteboard. You guys should do the same thing, or maybe some scratch paper, and let's try to map this out. I'm gonna talk it out and not show you what I'm doing until a little bit later when we're finished, then we can compare notes. Remember that to learn physics, you actually have to do the physics. You can't just listen to me. Got to actively think about it and try it yourself. And then honestly, you're going to make a bunch of mistakes. That's normal. And then check your work and learn from those mistakes. And that's kind of the most powerful part of the process. So starting out, it says stationary close in front of me for 1 second. Well, I'm going to place myself at the origin. By the way, the y-axis on this is distance and the x-axis on this is time. So close in front of me for 1 second. Stationary, so I'm looking at a flat line. I don't want my position changing at all. I'm going to make this 1 second wide, and relatively close to me in front of me means a very small positive number. So what I'm doing is I'm drawing in a flat horizontal bar up to the first second. Then it's gradually speeding up. Now that's accelerating, that's changing speed. So I'm expecting a curve, and it's headed away from me. So it's already in front of me. If it's heading away, it's headed in the positive direction. I'm going to say that distances are increasing, and they're increasing more and more and more. So I'm going to draw kind of an uphill curve here. Then it's maintaining that speed. A constant velocity pattern is when my line is just a steady diagonal with the same slope. So I'm going to do that between 2 and 3 seconds. It's slowing back down for 1 second. Now, a lot of people, when they hear slowing down, they're tempted to have the displacement graph come down. But let me ask you this. Our object was moving forward, slowing down. It is still technically moving forward. Our distances are going to continue to increase. They're just going to do so less and less and less until this graph flattens back out. And a flat graph, move my head, arcing, that's when it's stationary, the position is no longer changing over the last second of this graph. So now I'm going to show you guys what I drew, see if you got the same thing here. So this was a stationary section. This is also a stationary section. In this middle section, it's moving at a constant speed. This curve getting steeper and steeper shows me speeding up. This curve getting shallower and shallower shows me slowing down. And so we can take a motion graph and we can break it into steps to describe more complex patterns than just one thing at a time. You'll see this at an even fancier level later in the tutorial here. All right, next up. Here is an example of that. In this graph, we've got now a stack of graphs, distance, velocity, and acceleration stacked all vertically. Why can I do that? Well, check out what the x-axis is. It's time, time, and time. Those all should exactly correspond. So when we stack them vertically like this, by the way, in that specific order, distance, velocity, acceleration, we should be able to get events in one graph to match whatever event happened in the other graph as well. And that way we can look at some consistent changes across all three of the stacks. So what you can do with this is you can basically break the graph up into separate chunks, just like we just did. We had 5 different things happen in our previous graph. But here you can tell that if one graph is about to change, so is the other. And that's why those yellow dotted lines are important. They let us link up what's happening. So this is a great example of what we're going to be doing later, which is that you get some information about the graph, and you're supposed to figure out how the other graphs should correspond. I'm going to do this on my whiteboard real quick. You guys go ahead and copy this on scratch paper. I'm sorry I'm blocking out the view of the acceleration graph, but that's it's a blank, so no worries. So go ahead and copy down a distance, velocity, and acceleration graph. All the x-axis is time. Go ahead and put in those dotted lines in about the same spot. And then we're going to draw in the graphs that are up here. We're going to talk about them, work through them. And I'm going to switch to whiteboard mode because I got the same thing you guys have now. So yeah, here we go. All right, so in this graph right here, is my distance tending to increase or decrease? Well, these are positive values, those are negative values, so my distance is coming down, right? What that means is my velocity is going to have a negative value. My velocity should be taking away from the distances. And one thing I know about this straight line pattern is that the rise over run is a steady value. I'm changing the same amount of distance each time. That's telling me that my velocity is steady, constant. Okay, so my velocity is not changing, and I decided because these distance values are coming down, it must have a negative value associated with that. So I'm going to put in a constant, flat, steady value for that first chunk. Now, did my velocity go up or down here? Well, whatever value it was, it's still at the same value, still at the same value, still at the same value. We already said this is a constant velocity pattern. It's not accelerating. So with my acceleration graph, I'm going to just put in a 0 all the way across that first section. All right, next section right here, we got another 0 velocity. This is all flat right here. It's not going up or down over this time interval. So my acceleration must once again be 0. And if I'm not moving, then at this time right here, I'll still be there, I'll still be there, I'll still be there. I'm just not changing my position at all. I'm not moving forward, I'm not moving backwards. That's where we get a flat graph on our distance. All right, this last one's a little tricky. Are my positions in this third section, third time interval, tending to increase or decrease? Hopefully you're thinking, oh, this is headed towards the positive side of the number line. So they're increasing. I know that my velocities are becoming positive. And it starts out very shallow, which means, like, see that slope right there? It's barely going up over time. Like, you can wait a little while and it's barely moved. Later on, you wait that same amount of time, it's moved a lot more. So what this tells me is that my velocities are going up. So I'm going to put gradually increasing velocity right here. That's going to be a linear positive uphill line. And if my velocities are increasing, am I accelerating? Yeah, I'm speeding up in the positive direction. That's going to go with positive acceleration. So I'm going to put a constant positive in there. So this was a scenario. You're going to see a lot of this practice set up for you on Google Classroom. I give you information on one graph and you hopefully can talk your way through and figure out what should be happening on the other two graphs. Now, if you don't get it, that's okay. It's going to take some practice, but let's look at some more ideas that can help you solve this. You're not quite getting the narration aspect of it yet and just kind of talking your way through it. So yeah, we're going to go more into the slope and area actually towards the end of this lesson. Let's hold that thought. Okay, now we're going to look at some velocity graphs. In the first graph, where my head is right in the way, the value of the velocity is 0. Is the object moving? No, it's got no speed. It is not a moving scenario. Secondly, this one right here, this velocity is just a constant positive value. That means we're moving forward at a steady rate. We're not changing speed at all. So this is where we have speed, but we're not accelerating, not changing speed. And then lastly, this third one over here, we definitely are increasing our speed over time. This would be like your 0 to 60 miles an hour in 6 seconds or something like that for, you know, your quick, but maybe not super fast car. So again, this is patterns you've already seen, but last time we were talking about the displacement graph. This time we're talking about the velocity graph. All right, it is your turn now. Take a look at each of these 3 scenarios. Come up with your best explanation for what's going on. Pause the video to do that, and when you're done, unpause and I'll see if we came up with the same thing. Alright, in this first graph, this is actually the hardest of 3. Let me get out of the way there. We've got a positive velocity. So I'm imagining this as moving whatever direction I define as forward. It was starting out really fast, like that's 0, that's some big number. So it's starting out with a really fast speed in the positive direction. It's getting slower and slower and slower and slower. Right about halfway through this graph, the velocity is 0. There is no speed left. And now it's actually starting to turn around and come back the other direction. This is now backwards because it's a negative value and we're getting more and more and more negative. So it's actually now starting to speed up in the reverse direction. What does this describe? Well, check it out. Got a pen here. If I throw this thing up, right, it'll, you know, it's starting out upward. I'm calling upward positive. It's starting out really fast. It slows down, right in the middle, gets to 0 speed. And then it's now starting to come the other direction faster and faster and faster. So this goes with that velocity graph. On the second graph here, there is no speed anywhere. This thing is never moving. It's got no velocity, velocity 0. So this is just a stationary object. Lastly, this graph right here, velocity, third graph, I'm sorry. It's going at a steady rate for a while, moving in the positive direction, moving what we'd call forward. And then suddenly about halfway through, it jumps up to a much, much, much higher speed, still in the same direction though. So this is driving slow for a while and then instantly switches to fast. And you know, in reality, it might not be able to switch instantly, but sometimes you can get things pretty close just by hitting it hard enough. So yeah, we'll look at some of these discontinuities, see where the graph jumps. It's not a continuous graph. And we can model those some different ways in physics. So hold that thought if you're like wondering, well, how does it jump up all of a sudden? That's a very good question. Hold that thought for about a month. Okay, last up, we got some acceleration here. Now, what's the difference between this graph where it's not accelerating and this graph where it's not accelerating? Well, just because it's not changing speed doesn't mean that we automatically know what that starting speed was. So one of these could be like, it's not moving and it stays that way. And the other one could be, it's moving and it stays that way. These are both graphs where the velocity is not changing, but you know, one of them could be 0, the other could be non-zero. And here we do have acceleration. This is where the speed is changing. And I would say this is adding to the velocity, which doesn't necessarily mean that it's going to be going faster. That's going to be a weird idea. Let's talk about that right now, in fact. All right. So if I am moving with a positive velocity and I pair that up with a negative acceleration, that velocity and acceleration are opposites. And the acceleration is going to be taking away from the velocity, taking away from the velocity, taking away from the velocity. This is definitely a slowing down scenario. Slowing down. There we go. Okay, another option is velocity, acceleration. This is where we already have velocity in some direction. The acceleration is matched up with that direction. So we're going to get more and more and more velocity in that direction. This is definitely called speeding up. Lastly, we could have velocity going this way, and we could have acceleration perpendicular to it. And that one we're going to talk about way later. That is called turning. Occasionally a very useful thing to do. This is where you're reorienting your velocity, but not necessarily increasing or decreasing your speed. Okay, do the velocities have to be pointing this way? No, if I do this, what I said is still true. When the velocity and acceleration are mismatched, regardless of whether the velocity and acceleration are positive or negative separately, like we could have positive acceleration be slowing down a negative velocity. Important thing is I said one's positive, the other's negative. When they're mismatched, that's when we get slowing down. When they both match up, that's when we get speeding up. And if they're perpendicular, we get turning. So it doesn't matter if it's positive or negative acceleration. You can't decide if it's speeding up or slowing down right away. You also have to know what's happening with the velocity and whether they match or are opposites. So interesting thought there. Yeah, you can have negative acceleration speed you up. No, positive acceleration doesn't automatically slow you down. Wait, did I say that backwards? Maybe I did. You hopefully get the idea. Basically, like, don't go off just the fact that it's positive or negative and assume that's the same thing as speeding up or slowing down. It depends on how they're matched up. That goes back to our vector concept we defined at the very beginning of the video. Okay, so let's see here. Yep. Same three scenarios that we've already covered, only this time we're talking about acceleration graphs. And let's pause there and let's go to this idea. Basically, here are the stacks of graphs all matched up for the different three scenarios. Here, constant position, nothing is moving because we have no velocity and no acceleration. Here, we're moving at a steady rate. Our distance keeps changing the same amount each time. Like, if you're driving at 60 miles an hour, how far have you gone in 1 hour? Oh, 60 miles. What about 2 hours? Oh, 120 miles. What about 3 hours? Oh, 180 miles. So this is basically just that continuous change there. That's what this shows, that the velocity is constant or not changing speed. And then lastly, over here, we got changing speed, causing our speed to go up, which causes our displacement to go up a lot. Now you might actually start to recognize this. This is part of a parabola, a quadratic, an x squared term. You've seen those in math before. It's one of the simpler curves you guys have tackled. All right. Now, is there only one way you can curve these things? No. Since we mentioned that's a parabola, you can have parabolas facing up, you can have parabolas facing down, you can have the right half, you can have the left half. So we're going to look about this in 4 different chunks. And what I want you guys to decide is in which of these displacement graphs, so we're looking at the position, distance, or location, in which of these position graphs is the velocity positive? And hopefully you're thinking, well, if the distance is generally going up, that means we are adding to the position with our positive velocity. So this is an uphill graph in general. And this is an uphill graph in general. Like in general, the distances are getting bigger. So B and C have positive velocities. Meanwhile, same idea. These distances are tending to decrease in value. We're headed from a big positive number towards 0. So we got decreasing positions. This has to be associated with a negative velocity. Same thing here. Positions are coming down, negative velocity. All right, next question, which is which of these gets a positive or negative acceleration? Well, here, let's start out with this one. This is the easy one. Here we had a positive velocity. We already said that distances are increasing. And we can tell from how this is flat, not changing position very much at first, but later it's really steep. This is changing position a lot. So this is going from slow to fast. And if our velocity is positive, in order to speed up, our acceleration also has to be positive. This has a positive acceleration. Let's look at graph A now. This one, we said that the velocity must be negative because the positions are coming down. So this one's going from steep to flat, means changing position a lot, to changing position barely at all. This is going from fast to slow in the negative direction. This is a negative velocity slowing down. And in order to slow something down, we need our acceleration to be opposite our velocity. So if this is a negative velocity, it must have a positive acceleration. So both these are positive acceleration graphs. And by now you've probably figured out, oh, well, that's one parabola. Here's the other parabola. This must be where the accelerations are negative. And yeah, here we've got a negative velocity going faster and faster, so the acceleration must match up with it. Here we've got a positive velocity getting slower and slower, so the acceleration must be opposite it. So that's a great way to think about things. Whether accelerations are matched up or opposing each other will determine if the object is speeding up or slowing down in general. Real quick, we can tell when something's fast because on a distance graph, the slope is steep. Whether that's steep uphill or steep downhill doesn't matter. We can tell where the object is stationary because the slope ends up at 0, where it's really, really flat right at these points right here. So looking at the slope can tell us quickly about the overall speed of things. All right, let's keep going. Now, we just mentioned slope and area a couple times, mostly slope, because that's the easier one to work with. What slope gets us is the answer to the graph below. So right here, see how that's totally flat? Slope right at this point before it starts to curve up is 0. It's flat across. The velocity graph right here, answer is going to be 0. Right here, we got some, modest, relatively steep slope, and the slope stays the same throughout. That's why this is a positive value and stays that way throughout. The slope is getting shallower and shallower and shallower, and where does the slope zero out? Right here. Check it out on the graph below. The value of this is coming down, and it zeroes out right here. So basically, the slope up here determines the value down here. Can you tell that this now has a negative slope? It's coming down. It's getting more and more steep downhill too, right? That's why the velocities are getting more and more negative. And then gradually they flatten out. So we're headed back up to 0 here. And right here is where we're at 0. Right here is where we're at 0. So this is the slope. This is the value. Now, turns out same thing here. What's the slope of this? Some positive number. Boom. Answer to the graph below it is a positive number. What's the slope of this? 0. Graph below it, answer 0. What's the slope of this section? Some negative slope, right? I'm in the way again, but here you go. It's some negative constant value. How about right here? Ooh, I'm gonna stay in the way. Ready? What's the slope right here? 0. Hey, 0. Okay, what's the slope right here? Some positive amount? And yep, some positive amount. So you can use slope to think down a graph. Make sure you also always stack your graphs in this order: distance, velocity, acceleration. Let's think about this a second way. Slope is a rise over run. It's how much it goes up and down compared to how much it goes sideways. What are the unit labels, the way things are being measured on the y-axis? This is meters, right? And on the x-axis, this is seconds. So what if I get a rise over run? That's meters per second. That's the unit variable that we measure velocity in. See, velocity is measured in meters per second. Now what if I take meters per second, the rise, and I divide it against the run? If I make a ratio out of that, if I have the run, well, that's time again. So meters per second divided by seconds, that becomes meters per second squared. And so you can also kind of understand this in terms of dimensional analysis, checking the units on stuff. All right. One more idea, a little bit trickier, and we probably won't have time to do this in depth yet because this is getting kind of to be a long tutorial. But you can also think about the area under the curve. And it doesn't have to be a curve, that's just a calculus expression. What it means is from the x-axis to the line, go ahead and shade that area in. And however much area that has, it's the amount that the graph above it has changed by. So for example, I could get this width of this triangle, I could get the height of this triangle, and I could do 1/2 base times height, get that little red area for just this zone right here. And that's going to be some negative multiple because this height is negative. And what you notice here is that the distance came down by some amount. Right here, what's the area under the curve? Well, compared to the axis, there's really nothing under that line. It can't shade any space in. And by how much did the graph above it change? 0. So to the right here, I've got kind of a better illustration. You can basically find the width. You can find the height. For triangles, it's going to be half of that because we're not using this half of it. We're only using this half. And so for this one, for example, I'd say 4 times 8 is 32 times the half is 16. This is going to change the distance by plus 16 meters per second from wherever we were before that happened. Over here then, I've got a width of 6. I've got a height of 8. Okay, so that's 48. So this chunk of time, the distance graph would go up by 48 meters. So we'll maybe get some practice on slope and area later. We don't want to get too involved in that right now. There are some pretty good web tutorials out there for that specific skill out there too. All right, last thing we got to take a look at is we got these two equations called the distance equation and the velocity equation. And we're going to be problem solving with them in pretty short amount of time here. And what do they have to do with the graphs? Well, I'm just going to rewrite them real quick. So I'm going to just copy them on my whiteboard, and then I'll show you guys a quick rewrite. And I'm going to do that actually the way you've seen them in math first. So in math, you guys have seen y equals ax squared plus bx plus c. That's a parabola. You've also seen y equals mx plus b. That's going to be a line. Okay, what does this have to do with our physics? Well, first up, what's on our x-axis? Which variable were we using on every graph? We were using t's. So I'm going to replace the x's with t's. Oops, just kidding. There's no squared there. All right, and with this first equation here, what we're tracking is distances. We're going to have the location that you end up at. Ooh, I should go back one slide just a sec. Sorry, skipped something. So if you're looking at these equations, first thing that might weird you out is, okay, d is for distance, v is for velocity, a is for acceleration, t is for time. I think you guys are with me on that part. The i's and the f's, that stands for initial and final. So kind of over whatever word problem you're trying to simulate with this is the starting location, initial distance, and this is the ending location, the final distance. And is this the velocity you start with or end with? Well, remember that I means initial. We're going to use an f for final. So this would be your starting velocity. Your starting velocity over here is your ending velocity, final velocity. Okay, so that's something to just keep in mind real quick here. All right, let's jump back to what we're doing. So I'm going to say, okay, wherever we end up depends on where we start, and it depends on our starting speed times the time, which, by the way, that is actually related to that area idea there. And it also is going to depend on how much we're accelerating per time squared. Or we could say that our final velocity depends on how fast we started, as well as how much we accelerated over time. So what I'm trying to just show you here is that you've seen this math before. In physics, we just, instead of generic variables, we're giving it variables that match kind of the words we're using this math to solve for. So instead of like c, you got di, or instead of tx, you got t. But it's still the same math you should be familiar with already. Okay, so let's take a look at this in more detail. Now, one question for you is, what happens if you put a 0 in one part of this equation? Like, what happens if I have no acceleration? See this graph over here with no acceleration? If I have no acceleration and no velocity, I want you guys to remember that anything times 0 goes away. Like anything times 0, it doesn't matter what it is, anything times 0 becomes a 0. So if I had no acceleration, this entire term goes away. And this entire term goes away if I also have no velocity. What happens is then that the only things left are where I started and ended, and those two things are supposed to be equal. Okay, let's check this graph. Wherever we started is the same place we ended. So this pattern appears when you have no velocity, no acceleration, and this all simplifies down to just your starting position equals your ending position. There's a 0 here and a 0 here. Those pieces go away. Let's look at another scenario. If I'm not accelerating, so if I have a 0 here, then my starting speed and ending speed will definitely be the same, because the whole point of no acceleration means that I'm not changing speed. And lo and behold, right here, whatever speed we start with is the same speed we end with. That's kind of cool. Looking up at this distance graph. Okay, I'm still not accelerating. This piece goes away. What I've got is y equals mx plus b. Okay, so we got a slope times our x, and then we got an intercept. And so basically we're starting out at our initial position. That's acting like an intercept right there. And then, yeah, we're moving at a steady rate. That's when you get this pattern right here. And actually the slope of this graph is the velocity, the idea that we just talked about. Hopefully you're seeing some math connections there too. All right, now don't freak out. We're gonna get to the fancy one now. If I have acceleration, then I've got a y equals mx plus b. Okay, so this is the slope of this graph. Yep, we just talked about that. You can use slope here define the value here, or vice versa to some extent. So whatever acceleration we've got, it's going to define the slope of the velocity graph. And we're going to have it over time, getting us a new final velocity that's changed somehow. So this equation, when we do have acceleration, causes this linear pattern here. And if I have acceleration, that means now I've got something squared. Like you guys know, anything with the x squared in it's going to probably make a parabola in this simple case here. And sure enough, we've got a parabola here. So I just want to draw some connections between these equations we're going to be using and these graphs over here. All right, that is it. What I'm going to do, if you want to stick around, is I'm just going to do a couple on the handout here. Give me just a sec. DocuCam. Got one of the handouts I've got posted to Google Classroom. This handout is, I think, from one of the Arizona State modeling physics curriculum. Pretty good stuff. So we're going to just kind of jump around to a couple here. Let's do this one. So first up, some things I'm noticing. This distance is totally flat. Slope is 0. So right away, I know the velocity of the graph below is going to be 0. Let's explain that a separate way. Whatever position I started with, later on I check it, it's still the same position. I can tell that this thing is not moving. So I'm going to put in a 0 velocity there. And did that velocity go up or down? Nope. It's just the same 0 velocity the entire time, so there's no way I can be accelerating yet. However, this goes from flat to steep. Like we got a big change in position in a small amount of time by the end of this, which means we're speeding up. Which direction are we speeding up? Well, the positions are tending to increase. So would you say this is going to be a positive or negative velocity? Increasing position is going to go with positive velocity. So I'm going to put a dot here to show that this was flat at the beginning. The slope was 0, we weren't moving yet. And towards the end, we got a very steep positive slope. So I'm going to give this a big positive value. I'm going to connect those with the line. And one thing you might notice is, okay, now our velocity, it looks like our velocity is increasing at a steady rate. It's becoming more and more positive. We must have a constant positive acceleration to go with that. So there's one example here. Do another one. These are some harder ones because they're giving us the velocity graphs instead. This looks like a good one. Let's do this. Okay, so I'm gonna just pick some arbitrary starting point. We don't actually know what our initial position is from this graph alone, but that's cool. Just gonna start from the origin. That's kind of what the origin means, right? Okay, velocity is a positive number. And it's a big positive number. We're far away from the 0. So we must be going fast in the forward direction. What that means is we're going to be adding to our displacement rapidly over time. We're going to get a big change in position in a small amount of time. So what that's telling me is this is starting out really, really steep up here. We're going to have a steep uphill. By the time we get to this spot though, the velocity here is 0. So that's where we're just very temporarily, briefly not moving at all. And on this graph, what that needs to look like is a flat spot. So I'm trying to pick out curves right now. Remember, we could pick out this curve, this curve, this curve, or this curve. And I know that I need to be, this is positive velocities. I know this needs to be an uphill graph. So it's either this one or this one. Let's cross those off. And then I know that I want to go from fast to slow, which should be the steep to shallow one. So it's this curve right here. So I'm going to put that in right there like that. And right here, we're going from slow to fast. And we're doing so in the negative direction. That tells me that my displacements are going to be coming back down. And we're going to start out slow, which means flat. We're going to end up fast, which means steep. So I'm going to go a downhill curve, getting steeper and steeper. Now, on the acceleration graph, would you say that the velocity is tending to increase or decrease? Oh yeah, it's coming down. That's decreasing, right? And it's doing so at a steady rate. What that means is I'm going to just put constant negative acceleration all the way across the bottom there. All right, that should wrap up our tutorial. Sorry that went a little long. There is a lot of stuff involved in motion graphing. Some things I'm hoping you're noticing are that, let's see, here we go. Let's jump back to the beginning. Sorry, taking a bit there. I'm hoping you recognize that there are some patterns to this, and that if you have a multi-step graph, you can break it down into chunks. That these graphs do relate to the equations we're going to be using next, and that problem solving with slope and area can help you get the relationships between distance, velocity, and acceleration all over time. Make sure you stack your graphs vertically like that. And last thoughts, let's jump to the overall big pattern right here. This is, just to recap, this is not moving at a steady speed also called constant velocity, moving at an accelerating tempo, however, whichever direction those might go. This one's a little tricky because there's 4 different curves to talk your way through. By the way, in physics, for nothing's moving is at rest. So we call this scenario at rest, this at constant velocity, and this at constant acceleration. Here are those 4 different types of curves when you are accelerating. Always important to think through combinations of velocity and acceleration. When the velocity and acceleration have the same sign, either they're both positive or they're both negative, that's when we're speeding up. If they have opposite signs, that's when we're slowing down. And then third scenario we're not talking about today is turning when acceleration and velocity are perpendicular. And here we go, some equations to think through, which we'll be using soon. And that is it. I'll catch you guys later. Hopefully this helped out if you're either working from home or just need some review. Have a good night.